Hello everyone. Today we are excited to share our journey on Project Echo Mic 1, sponsored by SANCTUARI. In this presentation, we will take you on the exciting developments we've made on our post-release tracking device made for small mammalian species. Our technical directors on this project are Joe Moreira, the dedicated founder and board chair of SANCTUARI, and Chris Rothwell, an ELE graduate of URI and invaluable technical consultant of the team. Our team consists of two electrical engineers, myself, Alexei Andreski, and my partner, Grace Firth. SANCTUARI is a nonprofit wildlife care organization dedicated to improving wildlife survival rates by utilizing modern technology. SANCTUARI is privately supported without federal, state, or municipal funds. It is unaffiliated with other Rhode Island wildlife organizations. While there are some compact and lightweight devices available on the market that operate on very high radio frequency or various GPS technologies, there is a notable absence of mass-producible devices capable of adapting and optimizing themselves for specific environments by harnessing cellular and GPS technologies, particularly for small mammalian species. Currently, a substantial market exists for trackers designed for larger animals such as deer or elephants. Additionally, it is our belief that many companies specializing in animal tracking devices may not prioritize the potential impact of these trackers on the animals themselves. Our primary mission is to develop an unobtrusive device that seamlessly integrates with the animal, delivering long-lasting and precise results. The consumer demand for such small trackers from animal rehabilitation centers is substantial. This tracker would provide users the ability to track animals they have never been able to in the past. This project aims to integrate an integrated GPS cellular and compatible tracking device designed for small animals. Ideally, this device should weigh approximately 5% of the animal's weight for the entire unit, ensuring it remains unobtrusive to the animals. This multifunctional tracker is envisioned to operate seamlessly in a wide range of environments, spanning urban, rural, remote, and unoccupied areas of the United States, and even potentially the world. A paramount goal is to ensure that the deployment of this tracker does not impede the animal's natural movements and ability to carry out their tasks or lead their lives without interference, thereby allowing for discrete monitoring and research in various ecosystems. Our primary emphasis was placed on gaining a deep understanding of the communication protocols and tracking technologies while meticulously managing our power budget. Over the course of the semester, we actively engaged in hands-on testing of IoT and GPS evaluation kits, testing their implications on the power consumption of our devices. This exploration naturally pushed us into an in-depth research of power management integrated circuits, further enhancing our grasp of power efficiency. For our project, our aim is to craft an animal tracker that leverages a specialized module that can capture precise GPS location data and seamlessly transmit it either to an external device or remote server via a cellular network, all the while efficiently managing power budget to maximize the device longevity. This slide offers a clear visual representation of how these parameters interact and collaborate with each other. This visual demonstration serves as a vital foundation for understanding our later slides. In the next section, I will jump into the fundamental aspects of power budgeting within our designs. We'll explore the background of energy models, the limitations associated with conventional batteries, the role of power management in integrated circuits, and the advantages of incorporating supercapacitors into our solution. Creating an energy storage system for a lightweight, compact tracking device has its own set of challenges. Several critical factors must be taken into account during the design process. Firstly, we need to assess the energy storage capacity measured in milliamps hours in relation to the battery's mass and volume. Equally significant is the consideration of the maximum discharge capacity of the energy storage device, which dictates the maximum current a battery can deliver over a specific duration. Let's examine the commonly used CR2032 battery, known for its lightweight design and impressive energy density. Despite its compact 3-gram weight and reliable 3-volt output, it possesses a nominal capacity of 220 milliamp hours, rendering it a durable and efficient option. However, it's essential to consider the battery's limitations, particularly when it comes to its maximum discharge currents. The Sierra 2032 reveals its weakness in this area with a maximum postage charge of only 30 milliamps. Unfortunately, this falls short of meeting our design requirements. Instead, we recognize the need to integrate a rechargeable battery and incorporate a power management integrated circuit. This choice would enhance the device's energy longevity by efficiently managing the balance between the load and the power source. However, most power management integrated circuits that we found could only provide a maximum output of 60 to 100 milliamps, a value still significantly short of our requirements. This is where supercapacitors come to play. While they may exhibit voltage instability over extended periods, they excel in applications requiring high current levels. This advantage arises from their high specific power, allowing them to accommodate high current demands effectively. Combining both the great attributes of supercapacitors and power management integrated circuits, we have the EH301, which can provide an instantaneous max current output of 1 amp. This is well within our requirements, and it also provides a voltage in between 3.1 and 5.2 volts. And now I'm going to be handing it off to Grace.
Hello, as Alexi said, I am Grace Firth. I'm the second designer on this project. I mainly focused on the GPS and GNSS technologies, cellular technologies as a communication method, and research of hardware components. As we began researching telemetry methods and communication protocols, we found many different technologies and devices that would be applicable to our tracking device, but ended up being eliminated due to it not meeting our anticipated best outcome. PIT tags, or passive integrated transponder tags, would have provided us with an incredibly low weight and power budget, but would have detrimentally limited our range abilities. LF, or low frequency, was a viable option, but we found that there was very limited information on using LF technologies in small tracking devices. High frequencies have a few drawbacks, mainly unlimited range, less location accuracy, and the potential need to create a secondary repeating device to strengthen the transmitted signal. Though the potential for creating a working tracker using VHF technology still exists, there is a superior alternative that addresses every drawback associated with VHF. We are currently exploring a hybrid cellular GPS system as our primary focus. The system merges the strengths of both cellular and GPS technologies, offering significant advantages over high-frequency applications. There's also a range of hardware components that would meet our many needs, including our power constraints. GPS would give the tracker more accurate location information and a better range than VHF, but will require permissions of satellite use as a receiver. Our proposed hybrid system aims to harness the best attributes of both GPS and cellular technologies. This approach involves using GPS for precise location triangulation while relying on cellular communication to transmit location data. One key challenge we are actively addressing in the development of this hybrid system is managing power consumption to ensure the creation of a long-lasting tracker. After deciding on cellular as the communication component of the tracker, we had to begin deciding on a cellular communication protocol to use. The 4 communication protocols we focused on were LoRaWAN, NB-IoT, LTE-M, and Bluetooth. We decided to eliminate Bluetooth due to its limitation to urban environments, which did not meet our requirements, and also eliminate LTE-M as it's designed to support higher bandwidths, which would mean higher power consumption for our device. This brings us to our top 2 contenders, LoRaWAN and NB-IoT. LoRaWAN stands out for its exceptional traits in low power consumption and extensive range, while NB-IoT emerges as a strong choice due to its widespread availability and expansive coverage. LoRaWAN boasts exceptional coverage in Europe, but has not met the same standard in the United States, limiting our ability to transfer data effectively. Due to this constraint, our design favors NB-IoT due to its higher cell coverage and similar low power consumption capability. NB-IoT communication involves the use of SIM cards, essential for cellular connectivity. The decision on the final communication method is based on the intricacies of the SIM cards. 2 options exist for active SIM cards: a subscription to a provider like Verizon or a prepaid SIM card with limited duration. Compatibility issues may also arise with certain providers, making device registration necessary, a time-consuming process. Additionally, the individual activation of each SIM card may pose challenges for mass production of the tracker. Now getting into some of the specific hardware we have been testing, starting off with the Monarch 2 Nectar B GMO2S module, a cellular-capable component manufactured by Sequence. From our testing, the Monarch 2 could be a viable component, but there isn't enough evidence for it to be the component choice for our tracker, due to the issues we have experienced with SIM cards. What we have done successfully involving this piece of equipment is gaining a much larger understanding of AT commands, which controls the communication settings of the device. With an operable SIM card, this chip has the potential to work well with our design. For GPS hardware, we began testing the L96 evaluation kit. We were able to successfully receive location data, testing the coordinates accuracy against multiple different sources. The L96 also proved to have an amazing cold start when it was outside, meaning the time it takes for the module to acquire position data. The power inputs of the L96 have not been fully tested yet, but from what we have researched, it is low. Looking to the future in our spring semester, we have some key goals we believe we will accomplish. The first task would be to combine all the different modules we have been testing separately and begin evaluating how they work together as one device. This is key in being able to create the tracking device. The next task is creating an operating software aspect to the tracker. Our hope is to make the experience using our tracker user-friendly for rehabilitators. Lastly, we have a goal to create a smaller, more optimized power management circuit based on the viability of the EH301 in our design. We would like to thank Joe Morera and Chris Rothwell, our amazing technical directors, as well as Dr. Sunak and the whole Capstone team for all the amazing help you have given us. Thank you.